So children, just now we have discussed regarding the law of conservation of momentum. What is law of conservation of momentum? The total momentum of a system remains constant until no external force acts on it. If external force is 0, the momentum of the system remains constant. Okay, and we have considered an example for that also. So initially body is moving with some velocity, and after collision the first body velocity decreases, whereas the velocity of the second body may increase. So let us try to prove the same with respect to the derivation. For this, let us consider two different marbles of different masses. So first marble, let us name it as A, whose mass is given with m1 and whose initial speed be u1. Whereas for the second ball, let us name the second marble as B, whose mass is found to be m2 and moving with initial speed u2. So this is all before collision, the two marbles of masses m1 and m2 moving with speeds u1 and u2 respectively. Now after collision, means then they both because remember that the speed of the first ball is greater when compared to the speed of the second ball. Okay, so this let us consider. That means the first ball is moving faster, whereas the second ball is moving slower. So after certain time, the first ball will definitely collide with the second ball. So this is all during the collision. Once the collision happens, what happens means the speeds will change. Okay, initial speed of the first ball was u1, whereas after collision its speed has changed to v1. Okay, well, the initial speed of the second ball was u2. After collision its speed has changed to v2. Let us suppose that they both are traveling in the same direction, hence the impact, that means the collision collide with each other. So direction is there, speed is there, so velocity we can name it as. So two marbles m1 and m2 with initial velocity is u1 into, after collision the same two marbles m1 and m2, okay, speed has changed, the velocity has changed to v1 and v2. So based on that, let us conclude that. Let us try to find the momentum. So momentum of the ball A, momentum of ball A before collision. So momentum of ball A before collision is during this process. How much was that, children? Momentum of ball A before collision was found to be mass into velocity. Okay, so what is the mass of the first ball A? Ball A mass is m1 into velocity of the first ball is u1. So this is before collision for first body. Similarly, if you consider for the second marble, momentum of ball B before collision, how much was that, children? Mass of the ball was m2 and the velocity with which it is moving is u2. So momentum of ball A before collision is found to be m1 u1 and momentum of ball B before collision is found to be m2 u2. Now coming to the after collision. Okay, this is the first case. Second case, if you observe, momentum of ball A after collision, this was all before collision. Now after collision, let us see what happens. After collision, how much, children? After collision its velocity is changed to v1, hence mass into velocity, this is m1 v1, whereas the momentum of ball B after collision, second ball. Children, marble, I have replaced this marble as ball, don't get confused. Okay, m2 velocity is v2. Okay, so initial velocity of the ball A was u1, final velocity was v1. So initial momentum was m1 u1, final momentum was m1 v1. So now if you would like to find out the change in momentum of the first ball, change in momentum of ball A. How much is that, children? So final momentum minus initial momentum. What is the final momentum? After collision is final momentum, and before collision is found to be initial momentum. So final momentum is m1 v1 minus m1 u1. This is the change in momentum of the ball A. Okay, so that is m1 v1 minus m1 u1. Similarly, the change in momentum of ball B was found to be, what is the initial momentum of the ball B was m2 u2, final momentum was found to be m2 v2. So change is final momentum minus initial momentum, that is m2 v2 minus m1 u1. I hope the concept is clear, children. So we have tried finding out the change in momentum of ball A as well as the change in momentum of the ball B. Two different conditions we have calculated. Let us suppose that this process, the collision process, has taken place for some amount of time. Say the whole process was carried for some time t. So this collision has been occurred for some smaller time, that is t interval. Okay, so this process is being carried for an interval of t. Then the rate of change of momentum, children. So what is that? The rate of, this is change in momentum. Now I am trying to calculate the rate of change in momentum. Again for the first ball A as well as for first ball B, second ball B. Rate of change of momentum of ball A. Rate means with respect to time you have to consider. That is nothing but change in momentum upon time. Rate of change of momentum is nothing but change in momentum upon time. That's it. Okay, so this change in momentum upon time can also be written as something like this, children. So change in momentum of ball A. Change in momentum of ball A is how much is that? m1 v1 minus m1 u1 whole upon t. Isn't it? So the rate of change in momentum of ball A is found to be m1 v1 minus m1 u1 upon t. If you take out m1 as common, you will be left with v1 minus u1 by t. We'll write it later. Similarly, you can also find the rate of change in momentum of ball B. This is nothing but again change in momentum of ball B with respect to time. Change in momentum of B upon time. This is of A. Okay, so this is nothing but B change in momentum. How much, children? m2 v2 minus m1 u1 upon t. That's it. Okay, so these are the two different conditions we have just calculated. So the force exerted, let us suppose that the force exerted by the ball A on B, what I suppose is force exerted by ball A on ball B. Let us name this as F1. Similarly, the force, so this first ball exerts some force on ball B, that I name it as F1. Similarly, the force exerted by ball B on ball A, reverse. Let us name this as some F2. Okay, so according to the Newton's second law of motion, what my children? This is according to Newton's second law of motion. What does Newton's second law of motion says? The rate of change of momentum is directly proportional to the net external force applied. What is the rate of change of momentum of the ball A, children? Rate of change of momentum of ball A is nothing but m1 v1 minus m1 u1 by t, and this must be equals to the force applied on that. So this, hence according to Newton's second law of motion, for ball A you can consider that F1 is equals to m1 into v1 minus. So rate of change of momentum of the ball A can be written as m1 v1 minus m1 u1 upon t, or in other ways f1 can be written as, both the case m1 is common, take out m1 as common, then you are left with v1 minus u1 upon t. Similarly, for ball 2, if you consider, again the rate of change of momentum for ball B. What is the rate of change of momentum for ball B? It is nothing but m2 v2 minus m1, m2 u2, second case, second mass and second velocity, upon t is equals to the net external force applied by it. So this F2 is equals to m2 into v2 minus u2 upon t. Is that clear, children? Well, but this is all about, from second law we have defined F1 is equals to this value and F2 equals to this. But from Newton's third law, what is Newton's third law says? For every action there must be an equal and opposite reaction. So based on that, so what is Newton's second law says? For every action there must be an equal and opposite reaction. So from Newton's third law, if F1 is the force applied by first body on second body, okay, if F1 is the force applied by ball A on ball B, and F2 is the force applied by ball B and on ball A, then these two forces must be equal and opposite in direction. For every action there must be equal and opposite reaction. So this is an action part, this is a reaction part. They must be equal but in opposite reaction. This is all according to Newton's third law. So but what is F1, children? So F1 can be written as m1 into v1 minus u1 upon t equals to, this is minus of F2 is written as m2 into v2 minus u2 upon t. So simplifying this, we get this t and t. Let us eliminate this. Then you are left with m1 inside, take it inside, v1 minus m1 u1 is equals to m2 v2 minus m2 u2. So bringing this minus value the other side, we have m1 v1 plus m2 u2 is equals to, here already left with m2 v2, okay, and this is m1 v1 minus m1 u1 is equals to m1 v, yes, this minus is there, minus, let us indicate this, take this minus is common for 4, then we are left with minus of m2 into v2 is minus m2 v2, minus and minus will plus m2 u2. That's it, children. Well, so we have this minus m2 v2, bring the other side, we have m1 v1 plus m2 v2 is equals to, what is left over? We have m2 u2 and minus m1 u1, taking to the other side we have plus m1 u1. That's it, children. Well, so this is the total momentum before collision. Before collision, what is the total momentum? m1 u1 plus m2 u2. This is after collision. After collision, what is the total momentum? m1 v1 plus m2 v2. So that's it. Okay, rearranging the term. So let me write the whole term initially. Okay, so this I'll be writing properly here. So what is this? First m1, therefore this is m1 u1 plus this one is m2 u2 equal to, next I'll be writing this one m1 v1 plus, and next is m2 v2. So this is what we have observed. What is this, children? Momentum of ball A before collision. This is momentum of ball B before the collision. Hence m1 u1 plus m2 u2 is nothing but your total momentum of both bodies. Total momentum of both bodies before collision. Total momentum of both bodies before collision must be equals to, again this one, total momentum of both bodies after collision. Hence we can conclude that the total momentum before collision must be equals to total momentum after collision. Okay, children? Yes. Total momentum before collision must be equals to total momentum after collision. Children, one more thing I would like to tell you. Suppose after collision, here you go. So this is m1 u1 and this is m2 u2. After collision it was found m1 v1 and here it is m2 v2. Suppose after collision, instead of v1 and v2, if they happen to move with instead of v1 v and here also v, the bodies will stick together like this. Okay, the bodies after collision, if they stick together and move with common velocity, say v, then let us suppose what happens. So not with two different velocities. After collision they together go with some common velocity v. In that case, let us see what happens. Okay, the same case can be written as, if they stick together and the common velocity v1, final velocity of the first ball equals to final velocity of the second ball, together equals to v, then this implies m1 u1 plus m2 u2 is equals to m1 v plus m2 v. So what is that? m1 v plus m2 v. So what is common? V is common. So V, if you take out V, then you are left with m1 plus m2 into V. What is that? m1 plus m2 into V. So what is the common velocity with which they stick together and moving means this V can be written as m1 u1 plus m2 u2 upon m1 plus m2. So remember this, children, the common velocity which the two balls move together is found to be m1 u1 plus m2 u2 upon m1 plus m2. So this is the derivation for the total momentum before collision, whereas the total momentum after collision. Okay, children? So hope you understood this. So we have considered two balls m1 and m2. Initial velocities u1 and u2. After collision the velocities has changed v1 and v2. Before collision momentum was m1 u1. For this second ball, before collision momentum was m2 u2. After collision first ball momentum is m1 v1 and second ball momentum is m2 v2. So change in momentum of the first ball is found to be m1 v1 minus m1 u1, and second ball change in momentum is found to be m2 v2 minus m2 u2. So rate of change of momentum we found out. Rate of change of momentum is because the whole collision is supposed to be happen for time t, then change in momentum by t is nothing but this value. Similarly for B. And now we have applied Newton's second law for this. According to Newton's second law, the rate of change of momentum, so this is nothing but the rate of change of momentum is directly proportional to the net external force applied on it. So the net external force applied by first body be F1 and second body be F2. Then F1 must be equal and opposite to F2. This is what according to Newton's third law we have applied. After solving we got that the total momentum of the two bodies before collision must be equals to the total momentum of the two bodies after collision. Suppose after collision if the bodies stick together and move with a common velocity, then its velocity is found to be m1 u1 plus m2 u2 upon m1 plus m2. That's it, children. Well, so based on that let us try to move with understand a few examples based on that, that is the rocket principle, the boat concept and the trigger gun. Okay, well,